Welcome back to my YouTube channel. I'm Chavi Shastri, and this is the fifth video of my video series Data Science using Python. In this video, we will learn about model evaluation, which includes how to perform model evaluation using Python, accounting for unequal error costs using Python. So, here is the first presentation. So, model evaluation, a comprehensive guide. This presentation explores the crucial aspect of model evaluation in machine learning. We will dive into various performance metrics, methods for evaluating different model types, and best practices for handling imbalanced datasets and optimizing model sections. So, join us as we delve into the critical process of ensuring your machine learning models deliver accurate and reliable results. So defining model performance metrics. So there are four parameters: accuracy, precision, recall, and F1 score. So what is accuracy? The overall proportion of correctly classified instances useful for balanced datasets but can be misleading for imbalanced datasets. And precision, the ability of a model to identify true positive instances correctly. It measures the proportion of correctly predicted positive instances out of all instances predicted as positive. And what is recall? The ability of a model to identify all positive instances. It measures the proportion of correctly predicted positive instances out of all actual positive instances. An F1 score, a harmonic mean of precision and recall, providing a balanced measure of model performance. It's a good choice when there is a trade off between precision and recall. So, these are the formulas for accuracy, precision, recall, and F1 score. TP stands for true positive, TN stands for true negative, and stands for false positive, and FN stands for false negative. So the formula for accuracy is TP plus TN divided by TP plus TN plus FP plus FN. Formula for precision is TP divided by TP plus FN, FP. Formula for recall is TP divided by TP plus Fn, and the formula for F1 score is 2 into precision into recall divided by precision plus recall. So evaluating classification models. Accuracy is useful for balanced data sets, can be misleading when classes are imbalanced. Precision focus on minimizing false positives, important when the cost of a false positive is high. Recall focuses on minimizing false negatives, crucial when the cost of missing a positive instance is high. FN score provides a balanced measure of precision and recall, useful when you need to prioritize both aspects of performance. So, evaluating regression models. There are three types of errors: mean absolute error, mean squared error, root mean squared error. The mean absolute error. The average absolute difference between predicted and actual values provides simple and interpretable measure of error. And mean squared error is the average square difference between predicted and actual values. Penalizes larger errors more heavily than smaller ones. And root mean squared error is the square root of MSE. Provides an error metric in the same units as the target variable, making it easier to interpret it. Handling imbalanced data sets. There are three ways to handling imbalanced data sets: oversampling, undersampling, and cost sensitive learning. So, oversampling is replicating instances from the minority class to balance the dataset. It can be done by duplicating instances or using techniques like SMOTE, which stands for Synthetic Minority Oversampling Technique. Undersampling is removing instances from the majority class to achieve balance. This can be done randomly or using methods like near-miss that selects instances close to the decision boundary. Consensitive learning is adjusting the model learning's algorithm to assign different costs to misclassifications. Cross-validation techniques. There are three techniques: k-fold cross-validation, validation, stratified k-fold, and leave out of cross-validation. So k-fold cross-validation is dividing the data into k-folds. The model is trained on k-1 folds and tested on the remaining folds. This process is repeated k times with each fold used as the dataset once. Stratified k-fold, similar to k-fold, but ensures that the proportion of classes in each fold is representative of the original dataset. This is particularly important for imbalanced dataset. So leave one out of outcross validation, a special case of k-fold where the k equals to the number of instances in the dataset. The model is trained on all but one instance and tested on that single instance. This is computationally expensive but provides an accurate estimate of the model performance. So, hyperparameter tuning and model selection. This includes three parameters: grid search, random search, and Bayesian optimization. So, grid search is evaluating the model's performance for a range of hyperparameter values. It systematically tests all the combination of hyperparameters and selects the best performing combination. Random search is randomly sampling hyperparameter values from a specified distribution. This approach is often more efficient than grid search, especially when dealing with a large number of hyperparameters. And by and last but not the least, Bayesian optimization using a probabilistic model to guide the search for optimal hyperparameters. It leverages past evolution to make informed decisions about which hyperparameter combination to explore next. So accounting for unequal error. First is cost matrix, second is weighted loss function, third is cost sensitive learning algorithm. So cost matrix. Cost metric is a metric that defines the cost of different types of errors. For example, the cost of false positive could be higher than the cost of false negative in a medical diagnosis scenario. Second is weighted loss functions. Modifying the model's loss function to assign hyper penalties to errors that are most costly. This approach helps the model prioritize minimizing errors that have a greater impact. Third is cost sensitive learning algorithms, which includes adapting the learning algorithm to accounting for unequal error costs. Some algorithms, like cost sensitive decision trees, explicitly consider the costs associated with different types of errors during the learning processes. So, it is a conclusion of this presentation. Model evaluation is an essential part of the machine learning lifecycle. By carefully choosing the right metrics, techniques, and strategies, you can ensure your model are robust, accurate, and reliable. Remember to consider factors like data imbalance, error cost, and hyperparameter tuning to achieve optimal model performance. So this is all with this presentation. Now we are going on the practical implementation of model evaluation and accounting for unequal error cost. So this is the code for model evaluation. I already write it there. So we are running this code and yeah, the output of this code is this. And this is the code, sorry, this is the code for accounting for unequal error cost. This code. And on running this code, we'll get this output. So this is all with today's video. See you all guys in next video.